Wireless communication and networking. This is the lab number 2, and previously we saw some basics about the MATLAB, how to install it and how to use some basic commands and how to write some equations and how to make some basic plots. So that we saw previously, but in today's lab we will be seeing something more in detail. For example, if you have to plot some signals. Firstly, I will introduce you what signals are and some basics related to the signals, and then we will move on to plotting various kinds of signals. And after this lab, we will be good to go and start the basic communication model, which will be starting with the sender, and then it will be ending at the receiver, and we have to recover the signal that we have sent from the sender at the receiver. So I think there are some basic terms that you need to understand. For example, frequency, time period, and then I will explain you what a signal is. Then different types of signals. There are periodic signal and aperiodic signal, the difference, deterministic signal and stochastic signal, the difference, and then what is analog signal and what is the digital signal, why do we need digital signals. So I'm going to explain you all these details now. First, so once you get some insight of everything related to signals, frequency, time period, and everything, then you will understand the communication model basics. And then in the same lab, in today's lab, we will also be covering some signals, continuous signals, and also we will be plotting the discrete signals using the MATLAB. Okay, so before starting the MATLAB, I'll share my other screen and show you some basics that are related to the signals. So I will stop my share screen. So I hope all of you can now see my screen, right? Okay.
Yeah.
So I'll start from the very basics. First of all, I think you may know what a frequency is and all these things are, but it's just for those who doesn't have any knowledge for these things. So I'll start from the very basics. Okay. So uh, firstly, what is a frequency? Frequency is the number of cycles completed per second. So this is my axis in time, and this is my axis in anything. So this is, for example, f of t. Okay, so what is frequency? For example, this is 0 0.1, 0 0.2, 0 0.3, and finally this is my 1 second. Then the number of cycles completed per second is my frequency. So if I see it here, I have one cycle completed here, then the other cycle completed here, and half of the cycle is completed here. So 1 plus 1 plus 0 0.5. So it is 2.5, and the unit of frequency is hertz. Okay, so the number of cycles that are completed per second is called the frequency. Now, what is the time period? The time period is, for example, this is again my y-axis, this is my x-axis, this is in time, and I just want to confirm, can you hear my voice? Is it clear?
Yeah.
Yes.
Okay, thank you. So now this is the same thing, but in opposite way. What is the time period? And this is my f of t. So if I look at this thing, this is the time taken to complete a cycle, or the time taken by a frequency, is the time period. So if this one is f, then the t, this one time period, is equal to 1 over f. Okay, so how much time is taken? For example, this took to 0.25, so the time period here is 0.25. Clear? Now I'll move to a little more advanced concepts. Now, what is the wavelength? The wavelength and frequency is sometimes considered similar. This is called a wave, or it is also called a frequency, right? So for example, this is the wavelength. Wavelength is the starting point, for example, here, and when that start point occurs again, which is here, right? So this is the starting point and that is the ending point, and the difference between the two is called the wavelength. And wavelength is usually denoted by lambda, wavelength. Okay, so sometimes you need to compute the wavelength of a frequency. Now you understood what a frequency is, the number of cycles completed per second. So 1 second, how much cycles completed? That much cycle is that much hertz of frequency. What is the time period? The time taken by 1 cycle to complete. What is the wavelength? What is the length of that 1 cycle that has been completed here? Right? So I think this is very basic and you will have no problem at all. So frequency, time period, it is clear. Now let's move toward the signal, what a signal is. So signal, we usually hear this thing like Wi-Fi signal is weak, 4G signal is coming, 4G signal is not coming. There's a lot of things like signal related to the signal. The TV signal is there, this signal is there, but we don't know what actually the signal is. Maybe you know. So what is the signal? Again, let's talk about this thing. This is the time axis. Okay, let's say this is in second, and this is any function. So you know a function, it can be a mathematical equation, right? So for example, f of t, again, so I'm calling it f of t because this function is changing with respect to this time. Okay, so this time, you know, the time is always increasing, right? Here it will be 1 second, then it will be 2 seconds, then it will be 3 seconds, and so on. The time never stops. And when you have a value of 1 and you have, for example, an equation, for example, f of t, this is equal to sine of t, where t is equal to time. Okay, so for example, when your t is equal to 1, plug this value here in this equation. So sine of 1, let's say before 1 there is 0. So what is sine of 0? Sine of 0 is 0. So this value will be here. And when you have t is equal to 1, so for example, at this point, when my t is equal, no, I'm not plotting because I don't know what my f of t is. But when so my second is 1, I'll plug this value. What is sine of 1? And anything, any answer that come from here, that will be my that will be my this y-axis here. So my x-axis is 1, and what is my y-axis? So anything, for example, 0.5 or anything. I'm just assuming it shouldn't be, for example, sine of 1 should not be 0.5, but I'm just assuming. And then I have 2, for example, and then there will be some value, then 3, and then 4, 5, 6, something. And finally, I'll get a very smooth curve like this. And then this curve will go in decreasing order, and then it will be finally coming towards the that 0 point. If you look at this point in the polar form, it is 180 degree. This is 170 degree, 270 degree, and this is the 90 degree, and this is the 0 degree. So what is a signal? The signal is any kind of mathematical equation or any kind of function that is changes with respect to the other quantity. So here, what is the other quantity? The other quantity is time. So when the time is changing, this f of t should be also changing. If this is n, for example, some discrete intervals, I'll tell you the difference, what is n and what is t. But if it is like just a number like 1, 5, 8, 9, this is changing in at the x-axis, then this corresponding value, it should be changing at the x-axis. What if this is not changing? What if this is not changing? You have a zero value here, and this t is changing continuously, but your time is not changing. It is continuously 0, 0, 0, 0, 0. Do you know what signal is that? Anyone? That is called DC signal. So DC never changes, right? So anything, even if the time is passing, anything is happening to the time, it will be still remaining at zero, right? So that is our DC signal. Now let's coming towards our other signals. For example, this is my quantity which is changing, and this is the f of t which is also changing with respect to this quantity. And if you take the example of sine wave, it is periodic. So what is periodic and what is aperiodic? So periodic is a signal which repeat itself again and again at regular interval of times. So if I have a signal here, for example, this is my um, axis and this is my t, and this is my f of t, and this my this signal starts from here. It completed a cycle, but it doesn't stop here. It again starts and then complete another cycle, and the pattern never changes. It follow the same pattern, right? So this is the pattern number one, this is the pattern number two, and then there will be again a pattern number three, and everything is happening very periodically. So this is called periodic signal. Now, what is aperiodic signal? So I think you can understand now that any signal, sorry, yeah, why it is not writing. Okay. Any signal which is not repeating itself, for example, a signal like this kind of signal, right? Or maybe in, I can have a signal like this, or I can have a signal like this, or I can have a signal like that. Are they repeating itself? No, they are not repeating itself, right? So such kind of signal are called aperiodic signal, or they are not periodic. They are not repeating itself again and again. Now, if we give it in another term, this one signal, periodic signal, we can call it deterministic signal. Deterministic means they are predictable signal. Predictable means that we know right after this point, this signal will repeat itself the same way as it had done here before. So we know how the pattern of the signal should look like at particular time. So we can predict about this signal, and that's why it is called deterministic signal. Now, what is stochastic signal? Stochastic signal is, for example, this one or this one. We don't know what could be the shape of the signal in future. It can be anything. For example, you are talking. Have you ever recorded your voice on the voice recorder on Windows? When you are recording your voice, it shows like some pattern like this, right? Sometime increasing, decreasing, and it never repeat itself, right? So when it depends on the pitch of your voice, it depends on the how much loud you are talking, how much at low volume you are talking. So depending on your compression and decompression of your voice signals, it activate the earphone or microphone, and that microphone is then making electrical signal, and that electrical signals are not predictable. You cannot predict about those signals. They are random in nature, and those random kind of signal are called stochastic signals. So mostly in nature, we find stochastic signals. For example, you see something, right? So the visual signals are the camera. This you are recording something. So any output, analog output recorded from a camera, it would be the random in nature. or when you talk, that will be random in nature, and you cannot differentiate you cannot predict the future of that signal, or what is the periodicity of that signal, right? So any signal which cannot be predicted, that is called stochastic signal or random signal. Now, I hope these are very basics of the signal, and let's move to the analog and digital signal. Okay, I'll talk a little bit more about the stochastic signal. As I told you, that we have the signals that are always occurring random in nature, right? Then if the signal is occurring random in nature, then how do we process it? Because we don't know what is the periodicity of this signal. We don't know anything about, if we know this signal at this point, we cannot predict at the next second whether the amplitude of the signal can be here, or it can be here, or it can be here, right? So at that point, it becomes very confusing. At that point, we need to process this signal. By processing this signal means that you have to, for all the previous signal, you have to see what is the highest frequency. Now let me further explain what is the frequency, how the frequency is related to the signal. Now this is your time axis, and this is your f of t, and this is your stochastic signal. So I'm drawing any kind of stochastic signal. So a stochastic signal can have a random amplitude, and it can have a random frequency at any time, at any amount of time. For example, the frequency can be lower. Lower frequency means it takes more time to complete its cycle. Or this frequency can be very high. High frequency means it will take less time to complete its cycle, right? And it takes more time to complete its cycle. And again, this will have some medium frequency, which means that it is lesser than this one, but it is more than this one. And again, high frequency, low frequency. So if you see, there are different frequency component available there in the signal. At the same time, this amplitude is also different. Amplitude mean what is the height of that signal. So it can, for example, 0.3. I'm not writing the unit because I don't know what kind of unit is there. So it can be 0.5, that can be 0.7, that can be 0.1. So at any amount of time, the amplitude can be anything, and at any amount of time, the frequency can be varying. So when you are processing this signal, we will see it later in detail, but we have to care about the high frequency component available. What is the high frequency? As I told you, this one is our high frequency component available. Okay. I see my marker is okay. So this one is my highest frequency component available. So I will care about what is the high frequency component available there, and then I will take the sample from it. Okay, just remember why we consider the high frequency component, because we have to consider each and every point of this signal, and if we consider each and every point, then it means that we can also consider each and every point of the low frequency. Anyway, we will see these things later. So when we are doing some sampling part, then we will care about this thing. So let's leave it for now. But the stochastic signal means that a signal that has different frequency and different amplitude at any amount of time, and they are not predictable, right? So let's move on. Sorry. So now let's again talk about the uh, analog and digital signal. And here this things comes the continuous signal, which is with respect to time, and also discrete signal. So I'll show you what is the main difference between them. Analog signal. Analog signal, all the signal that I talked about, they were analog, right? You have a time, and then you have a function, and this function is changing with respect to time. And all these points are well connected, right? So these points are well connected. So this is called analog signal. When you have any, I'm taking the example of sine wave or sinusoidal wave because it's very easy to understand. The stochastic signals and those signals are difficult to understand. So I will always consider the sine wave for taking some examples. So the sine wave, if you look at this figure, it can be written as f of t, or I can say it like, for example, x of t, right? So if I'm not saying that it is not, it's x of t is also a function, right? And this is the time. So when the time is changing, we take every possible point of that signal, and then that kind of signal is called the analog signal. What is the digital signal? The digital signal is a bit different from the analog signal. We don't consider each and every point of the signal, but we only consider some of the points from that signal, like this. And how do we consider it? We consider at that particular time. So we consider these samples at this particular time. So can anyone tell me why do we need it? Why do we need the mm, samples of the signal? Why don't we need all the signal? Because all the signal means you have all the informations that are related to the signal. If you are talking, so any possible point that is related to your talking, it will be an analog signal. But then we take the samples of your conversation, and that will take only particular sample from your talking conversation, and then that will either be stored or it will be transmitted. In this case, for example, I am talking about the discrete signal. It will be looking like somehow like this. So can anyone tell me why do we need the this one? Why do we need this one? Why don't we use this one? Anyone?
Save storage.
Exactly, to save storage and to save resources, right? If you have to transmit the signal or if you have to store the signal, then what will happen here? Then it means that you are considering each and every point. So it means that you are also using the unnecessary points. And then, for example, this, if you want to store it, let's say, for example, it requires 5 GB of size, right? Or if you want to transmit it, you have to use more bandwidth for this one. But on the other hand, if you use the discrete interval of that signal, or you use only sample of that signal, it will still retain the feature of this signal. If you see, it still retain the feature of that signal. It still looks like that if you interpolate it, right? But you don't have to take each and every point. You consider fewer of its point, and that, for example, it was taking 5 GB of size, it would take maybe 5 MB. Just an example. It might not be true, but just telling you with how much size you can save when you are sampling the signal. And at the same way, if you need this much of bandwidth here, for example, you need this much resources here, here you will need this narrow bandwidth to transmit the same amount of information, the same signal. So what is the goal of communication? The communication systems basically try to convey the information from the sender to the receiver while retaining all the information and the good quality, right? So if you have a sender, this is my sender here, and I'm sending some message, hello, and their signal should be received at the receiver, and when the receiver receive it, it should be interpreted as he double lo, not single l, right? Otherwise it will, if there it is received as single l, it means that the signal is somewhere corrupted. And why it is corrupted? Because we have skipped some of the information. We were supposed to send something like this, but we sent something maybe like this, right? So some of the informations are missing. And why that missing happens? Because we did not sample the signal well. We did not sample it well. And how do we sample it? That is what I explained you just a while ago. We consider highest frequency component. Why do we need the highest frequency component? Because if you have a signal, let's say, now let me talk about a bit random signal, right? You have a signal and it has the different frequency component, and then it has also a big signal, like big frequency. Now, why do we need only the high frequency component? And then there is a theorem which is called Shannon Theorem, Nyquist criteria. Sorry, there is a Nyquist criteria, and it tells you that you have to sample this signal at twice of the highest frequency signal. So twice of the highest frequency, f of h, for example. So highest frequency, right? So if you have this signal, right, for example, I'm not caring about the highest frequency, but I'm just sampling it randomly. For example, I'm taking one sample from here, then here, then here, then here, then here, then here, and like this. So when I am interpolating this signal at the receiver, I will get something like this. So do you think it looks like the signal which we send? We lose this information and we also lost this information, right? That is why we care about the highest frequency component. Highest frequency component, if we were having the same signal, for example, the same as the above I explained. Sorry about this. And yeah, now I have the same signal, which looks, I'll try to draw it again. And yeah, and now I'm caring about this signal. For example, this is my highest frequency signal component, right? So I will consider at least twice of this signal. So if I consider twice of that signal, it means that I am taking consistently taking the low frequency will automatically be counted, taken into account. But not only the low frequency, but also the higher frequency will be taken into account. And when we are recovering this signal, then we can almost recover every point of the signal, and we lose no information, right? Now, did you understand why do we need the highest frequency component for the sampling? Because we don't want to lose any information, right? We want that hello to be received completely. We need one L more there, right? For that sake, we have to consider also the high frequency component. So we cannot randomly just sample a signal. Any question so far? Right? Okay. So any signal where we takes every point of the signal, that we call the continuous signal, and a signal where we call only the discrete interval of that signal. We don't want to transfer all the information, but we need to transfer the reasonable amount of information. That is called f of n, and this at f of n will be denoted not in the parentheses like this, but it will be denoted in the square parenthesis, and this n denotes the discrete intervals, and this is called discrete signal. So this is my analog signal, and this is my digital signal. All clear so far? Any question here? Okay, so I hope everyone is clear about this. So now let's move to the first signal that we are going to plot. As I told you, our signal is nothing but some mathematical equation. So I'm considering a discrete signal, which is, for example, I have one value for the n greater than equal to 0, and I have 0 otherwise. What does it mean otherwise? Otherwise mean if n is less than 0. So if I'm plotting this signal, how it should be looking like. Let's say I'm not plotting the discrete. Let me say that, let me write it in continuous so that you can better understand. If I have this one axis, for example, this is my t value, which is increasing, and this is my negative t value. So any signal that is increasing after 0, it means that its value is 1. So here it is 1, right? and anything otherwise is 0. So the value which is less than 0 is 0, right? So my unit step function, it is called unit step function. So the unit step function looks like this. And how about the unit impulse? Have you heard about the impulse signal? So if I have to write about the impulse signal, let's say that is denoted by delta of n, and this is equal to the unit step function, which is my this function, and the unit step function but delayed by 1. What does it mean? Let me plot it. So this one will be looking like this. So if I have a value that is going from 0 to t, and the unit step function will be like this, and the unit delayed one delayed function will be looking like this, right? So it is 1, and after 1 the value should be like this. So if I subtract the unit step function from the 1 unit delayed function, how it would looks like? It would looks like something like this, right? It will be a peak at 1 and then it will be 0 elsewhere. So this kind of signal is called unit impulse signal. Clear? So now let's go to the MATLAB and see how these signals, how we can plot these signals. So I'll share the screen, the other one screen. So can you see my screen now? I hope you can, because I can see it on my other device. Okay. Now I'll open the MATLAB and I'll start with the new script. So every time you are doing something on the MATLAB, you have to open this new script from here, okay? So it will automatically open a new window for you. And although you can work here too, but it will, if you just put some, if you just restarted the MATLAB or something happened, all these variable will be lost and you have to do everything again. So we don't want to use that, right? We don't want to have that experience. So that's why you should be using the script window. So first of all, I will save it anywhere. For example, this is my documents and this is my test one, and I will okay, it is already saved. So as I told you, when you are starting the MATLAB, you should use these 3 lines: close all and clear all. So what is the function? Anything that is existing before in my command window, my workspace, or anywhere, or there are figures, clear everything. So it will clear it, and if I do it, see, there is nothing. Everything is quite clear, and now I can start my first program, first signal plotting. So let's say I am plotting my n sequence, and my n sequence is equal to, okay, there are 2 ways. For example, if I want to make something like n is equal to, I want to make an axis from -10 to +20, right? So one way is to write everything manually: -10, -10, -9, -8, up to a lot of thing I have to do, and finally I have to write like 181920. Yeah, this will not work because these dots are not recognized by the MATLAB. But if I do something like that, so um, these are missing, yeah, but you have to do everything manually, but we don't want to do that. So the easy way is to -10 colon, and then you will just simply write 20, and it will write this, it will do the same thing. If I use this function here, and if I show you, this is everything: -10, -10, -9. So with very few with one line you can do all that thing. Now I want to plot the axis, like the y-axis, so that it should be 0 when it is less than 0, and it should be 1 when it is greater than 0, right? So for that we have a functions which is called zeros, and zeros only plots 0 for us. So how much zeros do you need? Since the signal is starting from -10, right? So you need at least 10 zeros. So I will write like zeros from 1 comma 10, and it will write 10 0, 1 2 3 4 5 6 7 8 9 10. So 10 zeros. And then I will simply write that 1. I will then write 1 comma space and ones will write the number of ones. So how much ones I need, because it has to go from -10 to 0, and from 0 to 20, right? So in that case I have to write it like 1 comma 2 0, and if I enter it I have 20 zeros there, right? So I'll use this thing. For example, the unit step function is denoted by u, and I am writing it in the form of matrix. And then I will do the same thing, zeros, and then I will say that I need to have 10 zeros, and then I'll say that then I have 1, and then from 1 to 20 I have ones. So I will say that I have ones from 1 to 20. Right? So this function will give me some zeros and some ones. Oh, sorry, it is not a, it is 1. Right? Now it should be working. Right? So it is giving me zeros up to some point and then ones later on. Now I want to plot it, and I want to see, does it looks like the same? So let's say this is my first figure. I don't want to make a new script for each figure. That's why I will call it figure number 1. And I'll simply plot it as plot n comma u. So if I use the plot command, it will plot it in the analog form, and if I use the stem command, it will plot it in the discrete form. So I will use the hold on command. Hold on means that you are using the same plot for plotting the other one. So I will use the stem and the same variables. I have the intervals, which is n, and then I have the function u, unit step function, and that is it. And now what is my x-axis? So I will, let's say, write down x label, and the x label is the time or slash discrete intervals. And what is my y-axis? My y-axis is the unit step function. Unit step function. And that is it. And then I will just simply plot the grid on, and you should see a unit step function here. So you can see from 0 to until 0 it is 1, but you see that it will take some time to reach the 1, and finally it will be continuously like that value. The blue value, it is the continuous form, and the other one is the discrete form. So you have 0 values before 0, and you have 1 values after 0, right? So now how about I now try to make the unit impulse function that I just explained you earlier. So I will just type this one, and instead of 0 I will say that it is zeros again. So I should have only 1 at the middle, and I should have zeros before, and I should have zeros after, right? And then I will just simply use the, let's say this is the unit impulse, so I am calling it ui, and I am copying everything from here because all the things are similar. this is the figure number 2, and this is the plot U1 I, and also this is the UI, and then I will simply run it, and this is my unit impulse. So can you see it is only 1 at 0, and then it is 0 at the remaining. So the red dots are the red lines here. It is denoting the discrete interval, and the blue line is showing you the continuous one. Okay. So if you want to also use the axis command, for example, my axis should be not uh, more than this. Sometimes it will show you the axis starting from -15 and it will goes up to -20, but your data is lying in between -20 to +20, -10 to +20. So in that case, you can also type in other thing like axis, and then how much is the axis. For example, my axis is starting from -10 and it is going up to 20, and then keep the distance between each axis is 1.2, and like that you can now also see it. See, so there it will confine your data towards this axis. If you want to play with this figure, you can just take the zoom and you can make it higher like this. Or if you want to increase or do something more with the figure to make it more nicer, you can take this edit, and for example, I want to make it thicker, so I will click on 2, it will be thick. If you want to make the color, you can also do that. For example, if I have this one, I want to make it some other color, for example, the green color, so it will become green. If I want to make it thicker, it can become thick. If you want to make it some other, for example, steric, it can become steric. So you can do a lot of stuff here. Okay, so this was the unit step function, and now let's see in the slides which one is our second one. So I hope you understood this equation, right? Now moving towards our basic, which is most important one, the sinusoidal signal. So in sinusoidal signal, you have a sine signal, and the sine signal is the function of this argument. And what is there inside this argument? This omega is actually called the angular frequency. And what is the angular frequency? It is equal to 2 pi f. What is the f? F is the frequency, and 2 pi is the complete cycle. So in radians, it takes 2 pi to complete its cycle. And what is this phi? This phi is the phase difference. So sometime your signal, when you transmit it, it will start from 0, but when you receive it, it will be received at, for example, 1 or some other places. So there will be some shift in its degree, shift in its angle. So that phase difference is counted here. So to plot the sinusoidal signal, here A is the amplitude. What is the amplitude of your sinusoidal signal, and what is the frequency of your sinusoidal signal? So how much congested are, how much congested your signal is, and then finally, what is the phase difference between the two signals. So this you can do it here. Now let me go back to the MATLAB, and I will say this is a break. I had explained you right in the previous, so I want to talk about something very new. So you should then use the double percent sign. And I'm now plotting the sinusoid, and this is the spelling, and signal. For the sinusoidal signal, what I need here, if you look at the equation, I need the value of omega. What is omega? Omega is equal to 2 pi f. That means I need the value of frequency. Then I also need the axis. So what is my axis? For example, in this case, it is starting from 0 and it is going up to 40, right? And then the phase shift. If you want to give the phase shift, it's okay. Otherwise, just keep it 1 or 0. It's up to you. And what is the amplitude of the signal? So I need 1, 2, 3, 4. So I need almost 4 value to plot a sinusoidal signal, right? So let's do it there. Okay, so let's say I am starting with the interval, which is the discrete interval, and it is equal to 40. Sorry. So my discrete intervals are ranging from 1 and it is going up to 40 like this. And instead of 1, I will start it from 0. And then let's say my frequency is very low, it is 0.1 hertz, right? So my frequency is this one. And let's say I don't have any phase shift. So let's say my P is equal to 0. So I don't have any phase shift. I will put the colon because I don't want to see my values when I'm running it. And then let's say my amplitude is equal to 1.5. And now what is the argument? The argument is this one. The argument is 2 pi f of n plus phi. So this whole thing inside the sign is the argument, right? So let's say I'm calling it arg, and this is equal to 2 multiplied by pi. So the pi is the built-in function. If you put it here, it will automatically give you 3.1416 value. So you don't have to write the value of pi. It's already defined in the MATLAB. What is my f? F is this one, which is 0.1. And what is my n? N is already declared here, which is 40, 0 to 40. And then plus how much is the phase shift? There is 0 phase shift. So just if you want to write it, just write it. Otherwise, if you don't want, it's okay because the value is 0. And then let's say my value x, I am calling it x, the amplitude value is equal to sine. So the sine function is also defined there, and I will say that sine of arg, right? And now let me simply plot it. So for plotting, I should again copy this one and I will paste it here. This is my figure number 3, and it is n with respect to x. So this should be x, and this is the time slash discrete intervals. So if it is, I will plot it both in the form of continuous, and also I will plot it in the form of n comma uh, x. So actually, stem and plot, there are different interpretation of the same thing. So it doesn't mean that the thing we plot it is continuous or analog, and the thing we plot with the stem is the digital. For digital, you have to do a lot of things. You have to sample the signal, you have to quantize the signal, you have to encode the signal, and there, once we are doing the lab from 3 onward, then you will see all those steps. It is just to interpret the signal in two different way. How this continuous signal looks like, they are well connected, and how the discrete signals looks like. So this is just for your understanding. Okay. So what is the y label? Y label is my sine wave, right? Sine wave. And let me discard this thing. I don't need it anymore. And let me, oh, some problem. I am using plot nux. There is no such thing there. Sorry, it is x. And again, so can you see it? They are the discrete intervals, and this is your sinusoidal signal, right? So they are repeating itself again and again. So this is one cycle, the other cycle, third cycle, and fourth cycle. So here is the time period 1, time period 2, time period 3. So all those stuffs are, you can see it here, right? So now let's move on and just do something more interesting. What is the next one? How do we plot the real-time signal, which is the real-time exponential signal, and then we will go and plot also the discrete time exponential signal. Okay, so let's go and plot it. Am I too fast or you are following me? I will still upload this video on your iClass so you can watch it later. And I will also upload the materials. So you have to do some more practice. But because of the time, I have to move a bit faster. Okay? Is this okay for all of you? I want to hear someone.
Okay.
Okay, thank you. So let me now plot the real-time signal, right? So real-time signal. For the real-time signal, as you can see this equation, you have the amplitude, you have some number, anything, and then you have the power of that. So if you see the MATLAB has the exponential form, and it can be, for example, if you want to take the exponential value from 0 to 5, it can just simply give you the answer. But I don't want to do that. I want to show you how the exponential function looks like. For that sake, I will uh, consider some variables for all c alpha power n. So C is my amplitude. Again, I will start with the N is my discrete interval. I'm always choosing the N value differently because I don't want to confuse you with the previous N value, because previously I used the N value 0 to 40. Let's say this time I'm using 0 to 35. And then I have the alpha, which is the next one there, and the alpha is equal to, let's say I'm saying that it's 1.2, and you can assume it any number, and c is equal to, it's just a small number, so let's say it's like how about zero point 0.2, and then I'm saying that x is equal to, write exactly the equation that you saw there. C was multiplying with the alpha, and then the alpha was taken, the power was taken for the alpha. So if you look at, okay, here is one thing very important. You can, sometimes you have two things. One is a scalar and the other is a vector. So scalar is any number. For example, 3 is a scalar, 5 is a scalar, 6 is a scalar, right? A vector is in the form of array. So 1, 2, 3, 4, 6, for example, are 7. And yeah, you can, in this case, you can simply multiply this with that, but sometimes your case becomes more complicated. You have 2, 3 values here, and that has to be element by element multiplied, or you can say the dot product. So this value should be multiplied with this one, this should be multiplied with this one, this should be multiplied with this one. Or if you have two equal array, for example 1 2 4 6 7, another is 1 3 5 8 9, and if you want element by element multiplication, for example the first element of the first array should be multiplied with the first element of the um, second array, then the second element of the first should be multiplied with the second element of the second array, and likewise the fourth with the fourth, third with the third, fourth with the fourth. In that case, you need dot multiplication. And for the dot multiplication, you need something like this dot. And then you are taking the power of, for example, for every scalar. So if you look at this one, this is a scalar value. This is a scalar value. And you have more values here, right? It is ranging from 0 to 35. So it means that if you simply take a power of this one, it might give you some error. For example, I'm I'm doing something like this, and I'm c multiplied by alpha, and then I'm just simply taking the power of which is the n. So it will give you the sorry, c. Yeah, it was c, because this cannot take the power directly. So for that case, you have to do it element power. So these two multiplication power taken for the 0, then for the 1, then for the 2, up to the 35 separately, right? So this is how it works. If you write it the same equation, sorry, it is not capital C, it is a small c, and then it should be working, right? So you can see it like this. And now I want to simply plot it. So I will say that stem of n comma x, and then yeah, that's it. I think I should use the x label, y label, and grid on from the before. I don't have to type it again. And for this one, I should say that it is the figure number 4. So figure figure number 4, right? And I think that is enough, but this is the real exponent value. Sorry, this one. This is not assigned. Real exponent. And I will run it. See, this is your real exponential value, which is exponentially increasing. Is it clear now? So let's move to the complex exponential value. For the complex exponential value, let me show you here. Actually, the signal, this is the amplitude, then your exponent signal to the power of this one. But if you write this thing in the Euler form, you can split it into two components, the cos component and the sine component. So the sine component is the complex part of the signal, which is denoted by this iota. We usually call it iota or j, and this one is called the real part. So if you want to only plot this part, then you have to write real function, real built-in function of the MATLAB, and it will plot you the real part of that signal. And if you simply want to plot the exponential part, then you can also see the exponential part of that one, the imaginary part. Sorry, this is the imaginary part and this is the real part. So let's do it. And now we will be using an other kind of plot. This is called the subplot, and I will use, first of all, let me declare some variable. For example, omega is equal to some value, any value, for example, 0.015 or anyone, or let's say I'm saying that pi is already there, right? Pi value is 3.12. Sorry, omega is this term, this one. So omega, declare it any value. So omega is equal to 0.12, 0.15, let's say 0.15, any value. You just think any value and just plot it. Phi, this is the phase shift, and let's say I'm calling it that there is the pi is 180 degree, right? And 2 pi is 360 degree. So let's say I'm saying that there is the very uh, reasonable shift, like 6 divided by 6 part of the pi, and then I'm saying that the input argument. So what is the input argument? The input argument is omega 0t plus I, and this is the I is the imaginary part. So C is equal to, or I can also call it argument minus omega and plus phi multiplied by this term. If you see the imaginary term, which is j, so this is multiplied with the j term, and this that we can denote by the I. So multiplied it with the I, and now what is the amplitude? So the amplitude, let's say I'm calling it k is equal to 2, and I'm need some discrete interval, n is equal to 1 colon or 0 colon 40. And let me now plot this signal. So amplitude multiplied by exponential to the power of this. So I can simply say that k, let's say x is equal to, what is k? K is 2. So I will write k multiplied by exponential is the built-in function, and then I can say that it is the c, which is this one, and c is multiplied with the n. So n is the discrete intervals that I defined here. So it is from 0 to 40, right? And please remember, when you have to plot something x with respect to y, so it's for sure your x value should have the corresponding value y, right? So any corresponding y value should be belonging to some x, because y is generally the function of the x. So the dimension should be always equal. That's why you have to be careful about the dimension when you are dealing with matrices or anything in the MATLAB. And now let's say I will do the subplots. So I want to have the two rows in the subplot, and for example, one column in the subplot and the figure number first in the subplot. And then I will simply say that stem, and the real part, for example, I will call it R, is equal to real of x, and I can call it, since I is already used, so I am G. Let's say this is the imaginary part, and I can say that I am AG. This is, so both the real and imaginary are the built-in function. See, they are giving you the hint too. So I can now simply plot, for example, the n, which is my x-axis, and what is the real part. So I can say that this is the R. Okay, this is the real part. And if you want to put this x label, y label, just I will copy it from there, and then I will put it here. And this is the time discrete interval, and this is the real exponential value. And I can also say that this is the title, so I will call it the title, and this is the real part. And then I will simply copy this part and I will paste it again. And then did I put the figure? So which one figure is this? I think it is the figure number 4. So figure number 4. I hope it will not be conflicting with any. No, it is figure number 5. So figure number 5. And then it is figure number 2. And then it is the IMAG. So this one part. And I will put it here. And this is the imaginary part. Yeah, and then also copy it, paste it, and then run it. So this is the real part. Yeah, and this is the imaginary part in the Euler form. So you can see the basic difference of the real and the imaginary part. So play with the numbers and you will see different plot of it if you increase or decrease these values. So actually the Euler part shows it into the sinusoidal form, because both the one is this sine and the other is the cos. So it will be something like this, sinusoidal form. Okay. Now, so I think Ash, you should be doing some practice on this one, amplitude modulation. So the equation is there, and try to plot something like this. And I have also given you the detailed description of this one, and try to plot this one. And this one is the swift frequency. So swift frequency means that your frequency will become it will start from the slower, it will get congested, then again it will become slower, not slower, lower. So the frequency will be starting from the lower, get congested, then lower again, then again congested, then again lower, then again congested. For that you have to use the argument in the form of quadratic. So please try these two function. And if you had any problem, then I can, I'll do it in next lab if you had the problem with this, but you please try it by yourself, right? And if you did it, yeah, I'll give you the screen share, and you can also show your result so that the other can also see it. So is there any question in all the things I explained so far? Any question from anyone? Anything from the basics or from plotting the signals, sinusoidal signal, real exponential, different signals, and these? Okay, seems like there is no question, right?
I will send you an email.
Okay, yeah, sure. You can send me email. Thank you. So yeah, that's all for today. And if you had any question with the plotting this signal, then please ask me in the next lab when you come to the next lab. And first, I will plot you this signal. But I want you to do some practice. And for that, if you did it, it will be very good. I'll be very happy from you. But if you couldn't, then yeah, just let me know. I will plot it for you. Okay. So I think that's all for today, and I'll see you in the next lab. Thank you all.
Thank
Thank
you.
you.
Thank you.
Thank you.
Thank you.
Thank you.
See you next.
Thank you.
Yeah. Bye bye.
Thank you.